Ladies and gentlemen, it is a pleasure for me to welcome you to this fourth John Franklin Carlson lecture and to introduce our speaker, George Ohlenbeck, Professor of Theoretical Physics at the University of Michigan. Professor Ohlenbeck is going to talk to us on the subject, is there an arrow in time? Professor Ohlenbeck.
Professor Keller, ladies and gentlemen, I feel honored for being invited to give the Carlson lecture this year, and I'm glad that in this way I can keep alive the memory of Frank Carlson, whom I knew so well and appreciated so much during the many years that we collaborated at the Radiation Laboratory in Cambridge during the war. I must, however, also say that I feel a little bit embarrassed, as I told Professor Keller when he invited me, because of the very high standard that you have put on these lectures. You see, it is true, all right, that any physicist must be concerned and also feel interested in the social consequences and the philosophical implications of his work. But unfortunately, it's also true that the opinions of the great majority of the physicists about these matters are usually not particularly original or profound. And also, unfortunately, I belong to this class, in contrast to the previous lecturers, who certainly were exceptions. So, with these apologies, let me state the theme which I want to discuss tonight. You may know that the physicists maintain that the basic laws of physics are reversible in time, or to say it more learnedly, are invariant with respect to an inversion of the direction of time. Or, to say it more poetically, one can say that the basic laws of physics do not show the arrow of time. Now, the question arises then, how possibly the physicists can maintain that, while in fact there seems to be overwhelming evidence to the contrary. This evidence includes not only the direct evidence of our consciousness, the fact that we know very well that we grow older and that we have to die. It also includes all the facts of biological evolution. And finally, the evidence against it also includes a very fundamental law of physics itself, namely the so-called second law of thermodynamics. This law says that if one has a closed physical system, that this system always will go to an equilibrium state, or to say it again more technically, to a state of maximum entropy, and that it will stay in this state once it is reached. Therefore, also even a physical system seems to show the arrow of time. Now, of course, there must also be strong arguments to the contrary, because the physicists are, of course, not crazy. They may be squares, but they are not crazy. These arguments come originally from mechanics. If we look at the motion of some object, particles or planets or whatever you want, under the influence of the forces between them, then by reversing the velocities, one will see that the path these particles describe will just be go backwards and will retrace themselves. You can also say, by making a movie of the motion and running the movie backwards, the reverse motion is then a motion which also fulfills the Newtonian laws of mechanics and is in no way fundamentally different from the original motion and cannot be distinguished from it, really. Now, this remains true for the generalizations of mechanics made in the modern times, the quantum theory and also the theory of relativity. Both of these very wide generalizations have not changed this basic feature of the reversibility in time which classical mechanics showed. And it is the great weight of the evidence of these theories which has led to the conviction that the reversibility in time, which says therefore that there is no arrow, is true for all phenomena on the molecular level. I should perhaps say, although perhaps some physicists were somehow axiomatically convinced of this, that there were quite a number who always have kept an open mind about it. And especially 2 years ago, when there was another basic symmetry law, namely the equivalence of right and left, or the so-called parity invariance, when that was first questioned by the Yang and Lee, and then was actually disproved by experiment, it was clear that immediately also the reversibility in time, or to say it in short, the T invariance, was again scrutinized. And people were very doubtful about it. But then, relatively recently, very delicate experiments, which I will not try even to describe for you, have shown that it is extremely likely that even in those phenomena for which the parity invariance is not true, that there the T invariance remains true. So there is at the moment no argument to doubt that on the atomic and on the subatomic level, all laws in physics do not show the arrow of time. So there is definitely a conflict with this prima facie evidence that I mentioned at the beginning. And it is clear that for the physicist, the first task is to resolve the conflict of this reversibility in time with the second law of thermodynamics. The problem to do this was first posed in all its generality by Boltzmann, and I always call it the problem of Boltzmann. He struggled with it his whole life. And I will try to explain with words and with my hands, if possible, the ideas that he developed, because they have remained completely fundamental in the whole further development of physics. Well, the two sides of the dilemma, namely that on the molecular level, all laws do not show the arrow of time, while when we look at it as a whole, it seems to go to an equilibrium, is of course due to the fact that the two ways of describing the systems is different. In the one way, you describe really the motion, or think of the motion of the individual molecules, while in thermodynamics, you look at the description of the system as a whole. It is the contrast between the microscopic and the macroscopic description of a system. Well, to bridge this gap, Boltzmann introduced the notion of probability in physics, which was also a very grave and important step. And by doing that, he was able to understand and also reconcile the difference in the temporal behavior of the two ways of describing the system. Now, to show how this can happen, I always use, since I learned it from Ehrenfest, I always use a model of Ehrenfest, which is a simple probabilistic game to show how apparent reversibility in this, on the molecular level, still can be in harmony with irreversibility when you look at it as a whole. Well, now let me explain to you the game which Ehrenfest proposed. Consider two boxes and say that you have 100 numbered balls which are distributed over these two boxes. When Ehrenfest was in exuberant mode, they always, instead of calling these boxes, he called them dogs. And he used instead of balls, he says there were fleas on the dogs. And there was a certain distribution of fleas over the two dogs. Since then, it is always called the dog-flea model. The game that we play is the following. We have a sack with tickets which are also numbered 1 to 100. Then we draw out of the sack a ticket and read the number. And as soon as that number is read, then we transfer the ball with that number from the one sack, from the one box to the other. Or you can think that the flea then jumps from the one dog to the other. Then we put the ticket back in the sack and stir it good. Make a second drawing, read the number again. Again the flea has to jump. Do it again, do it again, do it 1,000,000 times. Think that you do it really extremely long times. Now, suppose now that originally all the balls were in one box, say an A. Then it is of course absolutely sure that in the next draw one of these balls will have to go to the other because every ball was in the first box. After that, there is a chance of 99 to 1 that again you will draw a number from a ball in the box A, and that therefore a second ball will jump to B. Well, it is quite clear, I hope, that there is therefore a definite tendency of the number of balls to be equally distributed over the two boxes, that there will be a 50-50 distribution of fleas over the two dogs. That will be equilibrium. Then both will be just as uncomfortable. It is also clear that once you have reached that state, it will vary a little bit, but as soon as it gets a little bit away from it, it will equalize again. Or, as we say technically, it will fluctuate a little bit around the 50-50 distribution, but it stays on the generally close by the 50-50. Therefore, just as a closed physical system, it seems that this model goes to an equilibrium state and therefore shows the arrow of time. But in a sense, this is an illusion. Because suppose that you would always determine the difference of the number of balls in the two boxes, and that you would make a plot, or that you would make a long record of that difference every time you make such a drawing. Well, the difference will perhaps originally was 100, then it will tend to 0, then it will go away from 0 again, and so on. It will fluctuate around 0, and it is also true that since there is always a finite chance that you suddenly will make a long series of draws of tickets with numbers which were all in one box, that it may happen, simply a run against you, or a run against one of the dogs, that all the balls will still go practically back to one of the two. Since there is a finite probability That must happen once in a while, and if you wait long enough, it will, so to say, the number will therefore, as I say, fluctuate around, but it will, in the course of time, seem a kind of periodic behavior, because every value will come back if you wait long enough. Therefore, if you would make such a record of the difference versus the time, then such a record would not show the error of time. It would look the same way in the positive time direction as it would be in the negative time direction. Well, I will not elaborate this further. This is a very interesting question for the probability theorist. This is one of the nicest non-trivial models of a Markov process and can be completely discussed in all details, although it is not so simple as it seems, and in fact a complete solution was only given about 8 years ago. What I would like to emphasize, though, that there is here really a kind of harmonization of the two views. Although a very long series of observations of the difference of the numbers of balls does not show the error of time, the tendency towards the equilibrium distribution remains. One can say this sharper if one wants to. Suppose that you do this game not once, but that you have simply millions of assistants to your disposition. We call that technically an ensemble of assistants. And they all do the same game. They all start with 100 balls in one, all have their little sack, and they all play this game independent of each other. And then you could say that at every time, or at every stage, you could not look at the result of one game, but you could average over the results over your million games of all your assistants. They have, of course, to report to you, and you will then do the averaging. Well, if you would do that, it is easily to be believed, and it can be precisely proved too, that this average difference would simply go steadily to zero and would stay zero all the time. Now, there is one point which I should here perhaps still mention about this model, which might have occurred to you. You may have asked what the jumping of these fleas between the boxes, which is clearly governed by chance, what that has possibly to do with the motion of molecules, say in a vessel, which are governed by the strictly deterministic laws of mechanics. Einstein always used to say, der liebe Gott würfelt nicht. Our Lord doesn't play with dice. And it is, of course, just this question, which is really, I think, a very ticklish and controversial one, in which sense probability considerations and probability calculus can be applied to physics, which one has here still to say some words about. Not that I have a real complete solution. I think that in these cases there is really no mystery, although other people still think there is. You see, you can think of the following situation. Instead of this game, suppose that you play a game of billiards. Pool, you call it here in this country. Billiards is also to be supposed. But you do that not in an ordinary table, but a little bit funny looking table, so that there is not too regular shape. Therefore, suppose that you have such a funny-looking billiard tables, and let us also suppose that there is no friction whatsoever. It's an absolutely smooth affair, and that you have quite a number of balls there, which you start off with a certain speed. They are originally, say, in one of the corners, and you start them off with a certain speed. The one this way, the other that way, but very specific speeds, all of them prescribed. Now, what will happen then in course of time? I think everybody will believe that if this table is sufficiently irregular, that then, if you look a little bit later, you will find these balls all over the table, about equally distributed. Especially if there are lots of them and they collide against each other and against the sides, and finally they will be all over, and there will be a little bit here, but about the same amount in another region. There will be a tendency, as we say, to the uniform distribution. Now, I think this can be believed. It is remarkably that this problem can actually be calculated too, and there are people who have done that with about 250 billiard balls. They have not actually done the experiment, but they start them off with certain speeds and then let them collide, wait so that they collide millions of times, and really calculate precisely where they go at every moment. It seems a hard job, but with the computing machines nowadays you can do anything. Mr. Alder and his co-workers in California have actually done this, and then shown very clearly that there was this tendency to the uniform distribution of these billiard balls if you just follow the motion over millions and millions of collisions. Now, therefore, the motion of these balls over the table again shows a tendency towards equilibrium, which is now the uniform distribution. But on the other hand, it was proved about 50 years ago by Poincaré that as a consequence of the fact that the equations of mechanics are reversible in time, that it must be so that if you wait long enough, you will finally see that all these balls will crowd back to their corner or very close to it, arbitrarily close to it. And you will find them all back in the corner. You have to wait pretty long. Not in your lifetime, when it are 100 balls, not even with 100 balls in your lifetime. But it will happen, you see. And it is therefore, this is what we call the Poincaré recurrence time, or the Poincaré cycle. It therefore happens that such a state will reoccur completely similar to this unlikely distribution of the balls over the two boxes. Also, as I said, since there is a finite chance of a bad series of drawings, also such an unlikely distribution over the two balls will reoccur. There is therefore, between the two cases, a complete analogy. It is in both cases so that if the deviation from this most likely or equilibrium state is large, well, you have to wait till doomsday till it comes back. But it will come back. And this recurrence time is extremely sensitive. Depends extremely sensitive on how far away from equilibrium, from the uniform distribution you are. And therefore you can say this whole contrast between this approach to equilibrium, while the basic phenomena are reversible, is a kind of a human illusion. It is just so that if the deviations are very small, then they reoccur very soon. And then nobody will think that you have here something irreversible or in conflict with the laws of mechanics. But if you had a state which is far away from equilibrium, so that the recurrence time is long compared with the time of observation or with the time of your life, then you will say, well, clearly, there you see an approach to the arrow of time before your eyes. It all therefore depends on the relation of your observation time to the recurrence time of the system. Now, there is still one question before I leave this point. Namely, there still is the question why the two models, namely the motion of the fleas over the dogs and the motion of the billiard balls, are so similar, although the one is done by chance while the other is governed by the laws of mechanics. The real reason is, I think, that a small change of the initial positions and speeds of the molecules will have enormous effect on the future path of all the balls. Therefore, suppose that you again commandeered your ensemble of assistants, and you make an ensemble of billiard tables, all the same size, and you say to them, start the balls off all the same. Well, they will do their best they can, these gentlemen, but finally, assistants are not perfect. They will do the best, but the one will be a little bit off from the other. And as a result, all of them, really, the result of the further motion of the balls will be from all of them different, because they just started it slightly different. And it looks, therefore, that then the results of the successive observations of these assistants has a kind of chance element in it. Again, an illusion. It is only because of this sharp dependence of the result. A small change in the cause has large effects. This is what Poincaré said, and this idea was extremely brilliantly analyzed by Smoluchowski in a paper which every physicist still should read. I think that these considerations show that strictly causal laws are not incompatible with probability theory. This, of course, does not mean that if you have probabilistic considerations in physics, that there must be causal laws at the bottom. This is a turning the statement around, which I don't believe in, but other people do. Well, this is therefore in a very superficial way, but I hope that you have at least understood what the way that Boltzmann found to reconcile the reversibility of the laws of mechanics with the apparent tendency to equilibrium that all physical systems show. Let us now turn to the much more speculative question whether the ideas of Boltzmann throw any light on the probably much deeper conflict between the biological and the physical evidence regarding the flow of time. Well, I will begin with a speculation of Boltzmann himself. At his time, it was argued as follows. If the universe is a closed system, and if it had existed an infinitely long time, well, then it must be in equilibrium or in the state of maximum entropy, and that was called, in the German discussion, the problem of the Wärmetod, of the heat death of the universe, and people got awfully worried about it. Because it is clear that if the universe is in perfect equilibrium, then nothing can happen anymore, and perfect equilibrium of the universe means complete death for everything. Well, Boltzmann suggested that perhaps it isn't so bad, that it could be that the universe was in complete equilibrium all right. But we now know that there are fluctuations. And he said, finally, the portion of the universe which is accessible to our observation is probably only a very small piece of the whole universe. And it might very well be that this piece just is not in equilibrium, was in a spontaneous fluctuation away from equilibrium, and really quite a distance away, and since it is small, such things must happen, and so it might be that that is the case. Then you say, well, why do we live then in that? Why are we so happy that we just happen to hit such a fluctuation? Well, he says, that's simple, because human life is only possible in such a fluctuation, and therefore it's no wonder that you observe it, because otherwise you wouldn't be there.